Hello, my name is Tom Coughlin, and I'm going to talk about the memory of cars. This is the first car that I had, or at least a picture of a car like the one I first had, which is a 1970 AMC Hornet. And I have some good memories of this, as well as some bad memories. It needed a lot of maintenance work on it all the time, but generally it got me where I needed to go. Wasn't fancy, wasn't pretty, but it worked. But that's not what we're talking about today. What we're going to talk about today is about drivers, about the memory used in modern automobiles. And we're going to look first at the drivers for automobile electronics, the developments around this, how this relates to the activities going on to create an Internet of Things, connected vehicles, various standards, things of that sort. Then we'll go into modern storage and memory technologies and how they might be used in automobiles. And finally, we'll give a sample of tear down and look at digital memory and storage as used in a particular application, an infotainment application, which is a BMW digital radio. First, let's talk about the drivers for automotive electronics and memory. There are many trends going on that are driving automotive technology. These include the move to electric and hybrid automobiles, connected vehicles where they have various radios that can communicate, and that requires, again, radios and antennas, but they can communicate for navigation information, but also for car-to-car communication and car-to-localized services and even into the internet. We also have function that is becoming more and more common, which is Advanced Drive Assistance Systems, otherwise known as ADAS. This involves the use of various types of sensors, cameras, and then capturing that content, storing it, and processing it, and providing machine learning based upon that analysis that can be used to help on driver assistance and potentially ultimately into autonomous vehicles, autonomous driving vehicles. And then there's the various information and entertainment functions, as well as the instrument cluster for looking at internal status conditions within the car itself. With regard to that information and entertainment, augmented reality is certainly a possibility where we overlay information about your local environment and things that are going on around you on top of a normal vision of things as they exist. Potentially virtual reality, especially for either car passengers or with autonomous vehicles, could even be used for everyone potentially in the car. And then there's a trend towards higher definition, higher dynamic range, richer color displays, both for vehicle information and also for entertainment purposes. And then finally, targeted audio, where there are audio systems now which can create interference patterns that can provide audio volume only in a certain area, so you can actually provide differences in the sound that are heard by all the occupants in a vehicle. Let's look a bit at some of the electronics in modern automobiles. The source here is from Clemson University, their Vehicular Technology Lab, and you can see here a great variety of different electronic functions that are now going on in a car. Just a huge ways in which electronics is now playing a role. And we can see creating more processing, more network connectivity, and then also storage and memory to keep this information and use it is all in automobiles. It's all a part of the growth of what's commonly called the Internet of Things, which is interconnected intelligent devices, which can include vehicles. It's a very, very popular topic in technology circles. It's being driven by the declining price and availability of microprocessors, as well as memory and other technologies, and lower cost and ever-present radios. These now are showing up consumer products ranging from thermostats to refrigerators and including cars. The convergence of ubiquitous processing with networking is oftentimes called the Internet of Things, and as a result of the proliferation of smart connected devices, smart things will be in our homes, on our roads, in our factories, in our gardens and in the air. And here's an Intel slide giving their concept of an intelligent car. Today they're saying car owners and buyers want the latest technology in their vehicles, and safety is a key. They say that 60% of roadside collisions could be avoided with half a second's warning. 90% of collisions could be avoided with a full second's warning. And in tomorrow, we could see 69% said they would like to use a semi-autonomous lane keeping system. 63% said they'd like to use car-to-car communication. And again, 63% said they would welcome a fatigue warning device in their vehicles, but it includes things like intelligent maintenance for the device, for the car itself, vehicle-to-vehicle communication, smart traffic environments, and the ability of the car to interact with road warnings, etc. And all this potentially could create huge amounts of data, with maybe over 152 million connected cars by 2020, as in some projections here. So cars will be a big generator of data, an important element in the emerging Internet of Things. So let's look at an Internet of Things data set and get an idea what this looks like. So while the amount of data from a network device may be small in itself, say a sensor with taking some simple readings, the resulting data set, including metadata generated with the data, can be much larger. Now this data set, including that metadata, is what is analyzed in big data analytics and adds enormously to the overall value of that raw data. Understanding and controlling access to metadata is one of the keys for protecting personal content. Looking at the size of data and the resulting metadata, let's say a 4-byte raw piece of data from a sensor, like a thermometer. That can be associated with 100 bytes of metadata, which includes time, location information, perhaps information about the sensor device itself, and it can also include accumulating data over time, sort of a logging functions. The connecting vehicles together and connecting vehicles with local services can provide a lot of potential customer as well as enterprise values. Those customer values may be things such as on-demand radio, video, news, weather streaming from the internet or local services, access to emails, social networks, etc., hopefully not by the driver. Analysis of the driving, traffic alerts, navigation, advanced navigation systems, recommendations systems, help with parking, restaurants, etc. Various remote functions, emergency services, roadside assistance, and also theft alert and control, and geo-tracking. It also can give you localized information that could give you warnings about the environment ahead of you on the road, and help you to maybe make choices to do something else, if that makes sense. That's the consumer side. Now from the enterprise side, allows service scheduling, spare parts management, warranty analytics, deal with recalls, various status sensors and monitoring of the device themselves, promotions, fleet maintenance, and interesting concepts such as usage-based insurance, basically where you pay as you drive. So there's various consumer as well as enterprise potential values in the technologies that connected vehicles make available. Now we mentioned before, talking about how much data can be generated. Truly autonomous cars would definitely involve big data and the analysis of that big data. Google autonomous car generates about 1 gigabyte per second. The average US driver drives perhaps 600 hours per year, so that would generate about 2 petabytes per car per year. And the number of cars worldwide will surpass 1 billion. So the potential size of data generated by autonomous cars, if these ever become common, is huge. And most of that data will end up being stored in data centers, that is the cloud, which also would end up doing the bulk of the analytics since they have the high performance processing available. So where is the memory going to be? Well, as we indicate, there's going to be a lot of stuff that may end up being in the cloud. It has to, of course, move from the vehicle through those connections, local networks, and into the cloud. But there also is going to be the need for memory and storage within the vehicle itself. There may be outages, and you want to have continuity. You need buffering, caching. You need some localized, very low latency memory in order to be able to make important driving decisions, etc., and to inform the driver. There also may be between the cloud, that is the big data centers connected to the internet, and the vehicles themselves. That connectivity between vehicles and between local services is oftentimes referred to as fog or edge. So we can have perhaps storage and functions with processing and storage that could exist in those local fog networks, as well as in the device, in the car itself, and also perhaps the bulk of at least accumulated data in these data center clouds. Now here's another view of the fog. So the data centers provide these clouds. They work through the internet, and they transact between various levels. There's almost an infinite amount of data, as indicated on the right-hand side, could be in the data center. We've got the core domain of where you're actually working with. That could be perhaps terabytes. In the edge domain, we might be dealing with gigabyte type levels, and then finally in the device itself could be megabytes or kilobytes, for instance, in the car. The fog computing allows you an architecture that extends and allows you to get localized low latency access to compute, networking, and additional storage resources, which can augment the local resources, in this case within the car. Now there's various things that are going on with regard to the development of connected vehicles and the technology and the capabilities and applications that make possible. There, for instance, is a U.S. Department of Transportation project on next generation connected vehicles. There also is work going on within the IEEE Standards Association to develop and extend, for instance, the internet standards into connected vehicles. For instance, there is a cooperative autonomous and automated driving standard, IEEE P2040 series, that's being worked on. And there also are work going on to coordinate IEEE standards to all the different types of communication. There, for instance, also is the IEEE 802.15 wireless personal area networks for wearables and other short-term wireless devices. And one thing we might want to think about here too is that within the car itself there is also a network that will interface with all the devices that the participants have and allow them basically to run their applications. There are many applications, CarPlay and others, which will work directly with the car, and use the car as an extension of other services and applications that they get with devices they carry with them every day. So basically you bring your environment in with you, your environment moves into your car, and can provide you a seamless experience from before you got into the car to when you get in the car. So let's start to look at some of the memory trends in automobiles being driven by these trends. The electrical and electronics share of the value added to a state-of-the-art vehicle is about 40% for traditional internal combustion engine cars at this time. That jumps to about 75% of the value for electric or hybrid electric vehicles. Now, the total available market for semiconductor memories in automobiles applications is expected to be well above the cumulative annual growth rate for the total memory semiconductor market. And currently, automobiles use about 5% or about 5% of the memory market now, but it's believed with all these new functions and capabilities that could grow to 10% or even higher, according to a recent Micron press release. Now let's look at a few Micron slides which are kind of interesting about the growth of memory in particular in these automotive applications. As shown on the left-hand side of this chart here, the total cumulative annual growth rate of memory in cars overall is growing at about 12% annually. If we look at different segments of that, the infotainment is again growing about 12%. That instrument cluster for internal telemetrics and a display of information on the car itself, that's growing about 15%. And the largest growing segment is this assisted driving capabilities, the ADAS, estimated to be growing about 20% annually. Now this infotainment in particular is something that gives many people, extra value, perceived value in their car. And this is particularly true for young people and also folks in Asia. In China, according to a survey last year, 60% would change brands if they found the capabilities that they wanted in applications, data, and media. And among under 40-year-old, 50% would change. Looking particularly at the infotainment code storage and the compute memory storage, where the code storage is where, of course, the code that runs the device is running, and the compute memory is the available memory for doing on-site processing. We can see a chart here on the left-hand side where we're showing the increase in the DRAM density, that is the overall compute memory density, and the code density projected from 2010 out to 2018. At the same time, we're showing that there is a decrease in the power usage and an increase in the performance with these memory devices. So increased demand for memory densities, both for the compute memory as well as code storage, as well as decreased power use and increased performance. These are being driven by the adoption of 4K displays in cars, low power requirements and fast boot with NOR flash, or now even SLC NAND flash, and not just a single display, but potentially multiple displays in the car for all the passengers. And in order to keep the power down, they may use a low power DRAM. Here's another one of these Micron slides where they're showing the infotainment storage progression. So we're looking at the raw storage density, which is that's a raw NAND or eMMC, and also the mass storage density, that is the larger scale storage capacity. Again, projected requirements going from 2010 out to 2018. You can see that it's approaching about 500 gigabytes of mass storage on these devices seen by 2018. This is being driven by integration with phones and other wearable devices we talked about earlier, and the assumption of user preferences and contacts, again, to personalize your car. Also, perhaps a movement to 3D maps, which should have higher density storage requirements, and streaming of content requiring buffering capabilities. Now, we are in the Bay Area at ground zero of a lot of basic automotive research, autonomous vehicle technologies and various other things as well. And most of the big auto companies have a research center of some sort. Auto companies or companies that are talking about becoming auto companies have research centers and development centers, and in the case of Tesla, even manufacturing in the Silicon Valley area. This is from a Wall Street Journal article back in March. And there's a lot of startup activity going on in automotive technology. A lot of this is software, but there's projections that in 2016, that first of all, the current investments have almost matched 2015 with about half the year, and there's projections that the full year could approach close to twice that total investment, according to CV Insights. And there's other interesting things going on in this area here. At the NVIDIA GPU Technology Conference this spring, they announced an autonomous race car and said that there was going to be Formula E races with 10 teams and 20 of these autonomous cars that those teams would program and race as a further development in autonomous technology, and a rather exciting and interesting development. NVIDIA also has a Drive PX autonomous car development platform, and there's an interesting fusion sensor, what they call sensor fusion, which Drive PX does. Can take data from 12 cameras as well as LiDAR, radar, and ultrasonic sensors using algorithms, and it can give a 360-degree environment around the car, which can provide knowledge of dynamic as well as static objects, and then using neural networks detect and classify these objects, and therefore providing useful features for the drivers and participants, or potentially for autonomous vehicles themselves. So we talked about some of the drivers and developments in terms of automotive technology. We talked a bit about the developing memory requirements and expectations. Let's talk a bit about the storage and memory devices themselves that are being used or could be used in automobiles. Before we do that, let's take a quick look at a way of looking at various types of storage and memory devices. This is from work that a fellow at IBM named Steve Hetzler and I did last year. On this vertical axis is something called the touch rate, which is the number of times that you can access all the bits on a device, say an SSD, flash memory, a chip, etc., over the course of a period of time, in this case a year. That's a log scale on the vertical axis. On the horizontal axis, we have something called the response time. That is the time from when you initiate a command, an activity, to when that command is completed and it's ready to do another command. That's called the response time. This also is given in a log scale, going from short times on the right to very long times on the left. And the touch rate goes from very low touch rates at the bottom to high touch rates at the top. So as you go up the vertical axis, you have more accessibility to the data and the devices. As you go to the right in the response time, you have faster access to data that you're looking for, or faster commands and activities you can do. However, there's a trade-off that must be made. Obviously, everyone would want to be in the upper right-hand quadrant, but as you move in that direction, there's a tendency for the dollars per terabyte of capacity to increase. And we can see here then at very fast response times, high accessibility, we're in a high IOPS region, which may traditionally be using volatile memories as well as other types of technologies. Then we're into a transaction region where we're not quite as fast as able to access everything as the high IOPS region, but still pretty quick. Going down towards the lower left, we then are nearline, what's called a semi-active, a cold active, and then an inactive region. So this is a way of thinking about different applications in terms of these important metrics of touch rate and response time. If we then look at and do an overlay of various memory and storage technologies on top of this, we can see that flash tends to work best in that high IOPS in the transaction region. In fact, the optimum point of operation here, where you get the best trade-off between response time and the touch rate, is generally right around the knee of that curve. The performance hard disk drives used today in enterprise applications functions well in that transaction space, although they are gradually being replaced by SSDs. Then we show where capacity hard disk drives, that they peak basically in that nearline region. And then technologies used for archiving and long-term data are like tape, are in this lower left-hand area in the inactive region. So we basically have shown a way of thinking about these different devices and their connections. Now, we mentioned before that these things have different prices. This is some information. LTO tape is not going to be used in a car, but the price there is lower than a hard disk drive, which is then again lower than the raw storage capacity on an SSD, which might be somewhere in the range of 5 to 10x of the hard disk drive. And this, of course, how this develops in the future depends upon the rate of growth in the hard disk drive technology and density, as well as the flash memory density. Now, automotive memory and storage, there are different types: SRAM, DRAM, and EEPROM, for instance, are used in operation and code memory. NOR flash, generally used for code memory. The NAND flash is an operating storage, and then NAND or SSDs using NAND flash and hard disk drives could be used for mass storage. Now, first we'll start off with hard disk drives. There are hard disk drives used in some automobile applications, and particularly in infotainment systems. This example here is a Toshiba storage product, which has capacities up to 320 gigabytes. It's a single platter SATA drive with 4,200 RPM and a transfer rate up to 976 megabits per second and a seek time of 12 milliseconds. They can handle temperatures between minus 22 to 185 in operation, and minus 40 to plus 203 Fahrenheit in non-operation. And they have specialized aerodynamic technology in the head sliders that allow them to withstand altitudes up to 18,536 feet, which is higher than any city in the world while in operation, and withstand up to 3G vibration tolerance during operation. So for a hard disk drive, it's a pretty impressive, rugged device. And again, this provides lower cost storage for mass storage of, for instance, media content used in an infotainment system. I talked to the Toshiba folks about that drive and about their future plans, because that was announced in 2013. And if you were to make a drive like that now, you could easily have 500 gigabytes in the same kind of package. They said that they're probably going to be moving to solid-state drives for future announcements for mass storage in automobiles. So while they may eventually be displaced, and of course these have long lead times used in cars, generally like a 5-year product life that you have to be offering a product and supporting it. This is the Advanced Storage Technology Consortium. This is basically similar to the ITRS roadmap for semiconductors. Shows the areal density projections for hard disk drives going out into the future using technologies beyond perpendicular magnetic recording, such as heat-assisted magnetic recording, and then heat-assisted and heated dot magnetic recording in the future, which could bring us from about a terabit per square inch products now to 10 terabits per square inch sometime after 2025. Now let's look at flash memory. Flash memory is non-volatile, and there are various companies that have focused on the automotive market. SanDisk, now acquired by Western Digital, is one of this, and they have storage solutions including autonomous automobile-grade SSD card and also a ball-grid array iNAND embedded flash drive. Also, Micron has automotive SSDs, and which can, with an extended temperature range and robust data protection features. They also are offering an SLC flash, NAND flash in automobiles that they're saying can replace NOR flash for code storage applications, both in a serial SPI configuration as well as parallel NAND, like shown on the right-hand side. Comes in a 1, 2, and 4 gigabit density, chip density. It has a 10-year data retention at 85 degrees Celsius, which is important for these automobile applications, particularly if you want to do code storage. Also very useful in fanless applications, which are common in automobiles. Now, here's a version of a roadmap for flash memory. This is beyond the, shows the lithographic stuff normally shown in the ITRS roadmap, but also showing the move from planar flash to 3D flash. Samsung, of course, started that trend back in 2013 with products starting to ship in 2014 and 15. They're in their third generation product with 48 layers in 2016. There's projections that they may be shipping 64 layers by 2017, and they have stated at the Flash Memory Summit in 15 rather, that they could see going beyond 100 layer 3D flash memory devices. Toshiba and SanDisk, now part of Western Digital, have joint plants, and they're now shipping their own version of 3D flash of 48 layers. Micron, in addition, is also shipping their version of 3D NAND. SK Hynix is talking about that as well. Of course, the move to 3D NAND is being pushed primarily by issues with being able to push lithography to smaller and smaller features. It's easier to go in a third dimension and relax in the lithographic features than to continue to push the planar NAND flash. However, these devices are somewhat harder to make. They require new fabrication facilities, and as a consequence, the equity in yield, equity in the price per gigabyte for planar flash and 3D flash is estimated to occur sometime in 2017, when they may start to offer some price advantage after that. So it involves basically a folded, vertically stacked NAND string. The cells are generated inside of contact holes generally, and that means you can reduce the patterning and lithographic feature requirements. As a consequence of that, you can get better wearing devices. They'll wear longer. They're easier to make. The yields are higher. The data retention is better as well. Besides flash, there are other solid-state non-volatile technologies that are being used in automobiles, starting to be used, including MRAM. There's a company called Everspin, which is basically the only company really shipping MRAM products now. And they have some products available primarily for buffering type of applications that are built for automobile specifications. In a report we wrote last year, we're estimating that the emerging non-volatile memory market, including MRAM, could exceed $2 billion by 2020. There's some other technologies as well, although it's probably not going to show up in automobiles anytime soon. Intel and Micron at the Flash Memory Summit in 2015 announced, just before that, announced their 3D crosspoint technology, which is a phase change technology that, like many of the other emerging technologies based on a word line, bit line, individual bit addressable device, it's also they feel that they can build this up into multiple stacks of vertical structure, and therefore get fairly high densities in this. Advantages: it's greater density than DRAM, so the cost per bit is going to be less than DRAM. It has higher endurance than flash memory, so it kind of fills a niche between flash memory and DRAM to perhaps create something closer to memory speed non-volatile memories. So we talked about the things that are driving automobile applications and how that ties into the memory needs. We talked a bit also about the memory devices themselves. Let's now go in and look at a particular application, which is a BMW i3 digital radio module. So before we get into that, of course, again, there are many applications for memory and storage in automobiles. They can use in various sensors and collecting data from sensors or in cameras. We have backup cameras and other parking cameras and various things that could be used. A lot of the advanced driver assist systems have many different cameras, which of course can collect quite a bit of data, and even getting into having LiDAR if you want to get into these advanced autonomous vehicles. Then we have telematics for the information on the car status itself, and we also have infotainment systems. So all these things could be examples of memory usage. In particular, we're looking at the infotainment as being an important user of memory and of mass storage in a device, and that's, of course, this BMW radio is an example of that. So on the right, we show a teardown of this BMW radio. One thing that is easily visible here is there is a hard disk drive, one of these Toshiba hard disk drives, just under the top plate there in that blown up picture. There also are various types of memory that are used throughout the boards in the system. And we looked at, this is data, by the way, from Tech Insights that does teardowns and reports on what they find in these teardowns. And this is a report that they did on the BMW i3 digital radio module. And this shows a cost breakdown for the different components, and all the memory combined, there are many different types. Was about 5% of the total cost. The hard disk drive used here, which I'll show a picture of later, added about another 6% to the total cost, and the rest of the system was about 89%. The total cost of this device was estimated by Tech Insights at $560 or so. Here's a picture of the main board, one side of the main board. You can see a lot of discrete components here. But you also can see in microprocessors, but we also see various types of memories, some SD-RAM memory, and transceivers, connectors, various sorts of that. So there's flash microcontrollers with flash memory in them. So it's the board has a lot of things going on it. And if we look at a schematic of the motherboard, we can see the interfaces with various memory and storage devices. For instance, on the upper right hand side, we show an interconnect board connecting to that Toshiba hard drive. We also show the various radios here, connecting the GPS radio and Sky Networks radio that they've got here. There also is memory associated, NOR flash, for instance, associated with the GPS system. There is, and also with the Marvell Semiconductor single-tip Bluetooth in the system for the Bluetooth antenna. We can see that there is memory, serial NOR flash memory used as connecting Xilinx FPGA. We also show various types of SD-RAM memory, DDR2 that are associated with an NVIDIA graphics processor here. So as you can see, there's many different memory devices being used as well as mass storage in this motherboard. Here's a picture of in this case it's a 200 gigabyte version of that Toshiba radio, that Toshiba hard disk drive used in this BMW digital radio. So here we can see the part number for this piece. We can see that the Tech Insights estimate of the cost was something in the neighborhood of $29 with a single platter 200 gigabyte 2.5 inch drive. So some conclusions. Future cars will generate more data than ever before. They're part of a growing development of interconnected smart things, often referred to as the Internet of Things. And this connectivity and also the drive to more driver assistance and sort of computational driving will generate large amounts of data, much of which will go into the cloud. That will drive the growth in data centers. Also, automobiles, because of this local connectivity and this connection into the fog, will be part of local networks, both within the cars as well as between cars, which could lead to new applications and uses, and also with local services that are on those networks. Automobile memory and storage are crucial parts of building these modern automobiles with these new functions. If you don't have any data, you won't be able to process and do things. And these technologies are moving, although hard disk drives are used today, it seems like we're going to be moving more and more to solid state for these applications over the next few years. In addition to the traditional volatile memories and non-volatile flash memories, there are some new entrants that are going to start showing up in automotive applications such as MRAM. On the other hand, again, much of the storage in the cloud will support these automobiles will likely be in hard disk drives. So even though we're going to see more solid-state storage in automobiles, those automobiles with all these new functions, capabilities, and processing are likely to drive the growth of more and more hard disk drives being used in these large data centers in the cloud. So with that, I'd like to thank you very much for listening to my talk, and I hope that you got something out of it. And at this point, I am ready to take questions. Thank you.